Hi, my name is Jason Williams. I'm the technical lead for Team CSIRO Data61 in the DARPA Subterranean Challenge. This presentation describes our team's approach and results. Just a brief outline of the presentation. I'll begin with a description of the team, the methodology that we used, the results, and then finish with some findings and conclusions. This shows the Team CSIRO Data61 robots and humans through the 4 events: Tunnel, Urban, our own cave testing, and Finals. We're a collaboration between CSIRO, contributing ground robots, SLAM, communications, navigation, and exploration; Emerson, contributing aerial robotics and associated navigation and autonomy; and Georgia Tech, contributing multi-agent coordination. This shows the evolution of the robot team through time. Here there's a few key decision points to highlight. The Styx integration event showed the inadequacy of our ground platforms. We responded by acquiring the Bio5 Ozbot Titan ATR platform. Tunnel showed the excellent performance of the Titan and the strain caused by dividing our time between many platforms, so for Urban we focused on the Titan. We also had major communication issues at Tunnel, which resulted in the switch to the reagent-based network. Post-Urban, we were convinced of the merits of tracked robots, but wanted a more reliable small platform, so we started development of the Dynamic Tracked Robot, or DTR, and ceased development on the Hexapod. We were experimenting with various updates of the Ghost platform in the background, but earlier this year made the decision to acquire Spots. At the final, we fielded a Bio5 Ozbot Titan with upgraded motors and controllers alongside Spot quadrupeds and a new hovermap UAV based on a Navi platform carrying an upgraded multi-camera perception system. The DTR was deprioritized in favor of the Spot and Titan, but we were still planning to bring them if we had a larger deployed team. Our perception pack is in its 4th iteration now and provides a spinning LiDAR, IMU, 4 RGB cameras, and associated compute in a single calibrated unit. These are now commercialized through our partner AutoMap. This shows an overall block diagram of the system, which we'll step through over the coming slides. First, we'll look at SLAM. Both the UGVs and drones are running Wildcat. It forms the basis of the multi-agent capability, allowing maps, objects, and navigation information to be merged on each agent. In this video, each submap is shown in a different color. We store global navigation and object detection information relative to each submap, allowing it to move as SLAM corrections are made. This shows the maps generated by each team during the final prize run, with orange marking divergent points, that is, those not within a meter of a point in the ground truth scan, and green marking non-divergent points. Wildcat operates by performing a continuous time optimization of the trajectory within a sliding window based on IMU and LiDAR. As points exit the sliding window, they're accumulated into frames, which are represented by multi-resolution circle features, as illustrated here. Mapping is achieved through a pose graph optimization, matching circles between subsets of frames using ICP. Further details of Wildcat can be found in the recent Tartan SLAM seminar by Kazra Kasusi. A link can be found in the description. Now we'll move on to the navigation capability. Our traversability analysis is built around OHM, a dense 3D voxel-based occupancy system. OHM runs on a GPU, which enables it to integrate LiDAR and depth camera streams in real time. OHM builds height maps, which incorporate the concept of virtual surfaces, surfaces which haven't been observed but form the boundary between free and unobserved space. The video shows observed surfaces in green and virtual surfaces in yellow as the robot moved through the cave during testing in Chillagoe, far north Queensland. OHM has been released as open source. Using height maps generated by OHM, our traversability analysis checks two things. First, the slope of the terrain under a footprint, analysing the resting pose of the object as it's lowered. Secondly, we scan through the map looking for step discontinuities which exceed limits. The result is illustrated on the right, with virtual shown in yellow, traversable shown in green, and lethal shown in magenta. Virtual surfaces provide a principled method for addressing negative obstacles. As the robot approaches the edge, it's able to plan onto the virtual surface, allowing it to continue approaching. When it gets close enough, the slope becomes steep enough to be lethal, revealing the negative obstacle. Our path planning is based around Hybrid A*, performing on-demand costing of robot footprints in X, Y, and yaw, shown here during our cave testing. We've recently introduced a narrow gaps planner, which allows us to pass through much narrower doorways, overcoming resolution limits of the existing planner. Now we'll move on to global navigation. Our global navigation aims to build a consolidated map of all of the traversable space that's been observed. Navigation maps are built for each Wildcat submap, and these are shared across ground agents. Each submap is decomposed into a sparse graph using superpixel methods. An example of the segmentation is shown in the colors in this video. Edges are added between overlapping superpixels in different submaps. The boundary of traversable space, including virtual surfaces, forms the traversability frontier, which drives exploration. Put together, our nav stack is able to handle complex environments in a general way. This is illustrated through our handling of stairs. Traversability frontiers cause the robot to be continually commanded closer to and up the stairs. Paths are planned accordingly. The planner does not distinguish between stairs and slopes with similar gradient. The spot robot needs to navigate downstairs backwards. This was achieved by applying a large penalty to forward motion down slopes. Hence, you'll see the robot go down slopes backwards as well as stairs. UAV exploration uses an efficient method for obtaining the boundary between observed and unobserved space without a dense 3D voxel grid. Here its operation is shown in the urban event. A similar method was employed at cave and finals with improvements to frontier selection. We'll now look at the multi-robot task allocation and user interface. Coordination of ground-based agents is achieved through a multi-robot task allocation framework based on consensus auctions. This allows robots to construct coordinated task bundles without any central broker. For example, the coordination between two agents continues when they have communications between each other, but not the base. Using the bidding mechanism, robots form bundles of tasks for execution. One of the challenges of this is the dynamic nature of missions, since exploration tasks continually evolve as the environment is revealed. We found that having multiple exploration tasks in the bundle was undesirable due to their open-ended nature, but robots can select multiple tasks of different types. Definition of tasks is another challenge. In our solution, each ground robot receives and reprocesses the navigation maps from each agent and forms its own independent set of traversability frontiers. Task bidding is modified to capture the equivalence of nearby exploration tasks from different agents. The robots default to autonomous operation through multi-robot task allocation. The operator can influence decisions by creating prioritization regions or manually assigning a specific task. There's also a full suite of more manual modes, such as waypoints and teleoperation. One thing that we added late in the piece was audio cues, which give the operator an indication that there's an event for a specific robot that they should take a look at. We wanted to be able to set our thresholds for object detection aggressively low in order to avoid misdetections as much as possible. To accommodate this, we developed an interface that lets operators rapidly review new detections of the various object types, be it visual, Wi-Fi, and gas. Each robot and the base runs a system called Mule, which implements a peer-to-peer distributed database. This allows one agent to synchronize with another in a distant part of the course and carry that information back to the base. Multi-robot task allocation takes care of the coordination, meaning that when it's time to synchronize, only one of the two agents needs to return. Finally, we'll look at the object detector. Objects are detected using the DNet deep learning-based object detector running in real time on the NVIDIA Xavier in the perception pack and on the drone. Visible points within the bounding box are calculated to obtain the 3D coordinate detection as shown in the image. The detector was trained on a dataset of some 30,000 images collected in a variety of environments. Emphasis was given to labeling images which caused failures during regular testing. This illustrates the operation of the DNet detector, showing proposed regions of interest along with the resulting object detections. This shows images from the 4 cameras on the Spot robot, where the back camera is mostly obscured by the navigation computer. The right camera shows the successful detection of a survivor in a cluttered scene. Similarly, this shows detection of a drill in the front camera, also from a Spot agent. Finally, this shows detection of a survivor from the Emerson drone. In order to avoid duplicate reporting of objects, detections of objects at different times and on different agents are consolidated into single object tracks. This reduces both the operator load and communications data. In the prize run, this reduced 4,800 raw object detections down to 200 tracked objects. This figure shows a backpack detection along with a list of other detections of the same object. This slide outlines some of the other hardware on the robots. The ground robots include gas sensors and Wi-Fi detectors shown in red and blue. The Titan features side-mounted comms node launchers shown in purple and a drone launcher for marsupial launch shown in green, while the drone features a hover map LiDAR payload and multi-camera payload running the same object detector as the UGV. This video shows the comms node launcher in action and the marsupial drone launch during weekly testing at our site. The comms node enclosure helps the nose to fall upright and provides raised antenna positions. The dropping mechanism drops to the side so as to avoid blocking passages and is housed within the platform footprint, a requirement that we learned during our cave testing. In terms of results, something we're particularly proud of is how we've consistently improved as time's gone along. We came 5th at the tunnel event and 4th at the urban event. The following video shows our own cave event where we did our best to match DARPA test conditions in a cave in Chillagoe, far north Queensland. Just as in a challenge event, the environment was unseen by the operators prior to the runs conducted over 2 days. Additional developmental testing was conducted over a 3rd day. Now we'll move on to finals. We placed first overall in the preliminary rounds and second in the prize rounds, tying for first on the number of objects detected and falling around 40 seconds behind on the tiebreaker criterion of the time of last detection. The following is our Spirit video, featuring the wider home team created at DARPA's request to cheer on our deployed team. This shows the ground agent trajectories in the prize round. The total distance travelled ranges from 210 meters for the AGV Rat, which detracked, to 760 meters for Bluey, the majority of which was autonomous and even out of communications range. This shows the post-process point cloud from all robots, overlaid on the ground truth point cloud provided by DARPA. The point cloud collected by each agent is coloured as shown to the right, demonstrating the small overlap in the regions covered by each agent. The subway tunnel is the main area that was not covered. We avoided sending ground agents there due to the falls experienced in the preliminary rounds. The operator's intent was to launch a drone from the far end of the tunnel, but the agent carrying the drone detracked and was disabled along the way. This video shows an overview of the run as seen from the operator base station. Two spots, Bluey and Bingo, are first to enter. Bluey is commanded into the urban area and closely managed to prevent it from leaving comms and entering the railway tunnel where it fell in the two preliminary rounds. This was quite time-consuming for the operator. The other agents are sent into the tunnel and cave sections. Bingo makes rapid progress into the cave section and quickly goes beyond communications. With prioritization areas sorted, Bluey continues toward the subway platform and quickly loses communications. At this point, the operator has turned his attention to Bear, with Rat struggling to move after dropping a track. Communications were briefly regained with Bluey, revealing some of the data it had collected from Bingo. A manual task assignment was made to send Bluey in the direction of Bingo. Attempts to get Bear through the cave tunnels to the large distant cave were unsuccessful, with the drone making contact with the tunnel roof, so another route was sought. The two other routes were blocked, one by a dynamic obstacle and the other by the disabled ATR Rat. The operator moved to the only available plan, to launch the drone in the smaller cave and attempt the cave tunnel without the drone on board. Racing against the clock, this was executed through a combination of waypoints and teleoperation, along with regular node drops, to maintain a good communications backbone into the cave. A communications link was eventually established and the base began to receive data from Bluey and in turn Bingo. The link was quite low rate and full data was not received. This is a complex slide, but for each robot it shows the planner in effect at each time, the behavior in effect at each time, and the FSA state, or the executive controller state. A few observations can be made. The two spots were in autonomous operation for the majority of the run. As it turns out, most of that was out of communications range. Bear was under waypoint control for the second half of the mission when it was the only operational agent within communications range. The middle bar for Bear shows the period of teleoperation when the operator has the urgent priority task of relocating Bear to re-establish communications with Bluey and Bingo. The top bar for the two ATR robots shows the regular use of the gaps planner, making progress possible in tight tunnels. This video shows the communications network maintained over time using data recovered from each agent. We see Bluey entering the urban area where communications weren't great, as shown by the color of the link. We see Bingo reaching the far cave and losing communications. The link is shown until it's dropped off the communications network, which is significantly later than when the link is able to carry meaningful data. Bluey heads towards the subway platform. By this time, the link is unable to carry meaningful data and is under autonomous operation. Soon afterwards, it establishes communications with Bingo and starts downloading its data. It's assigned a task heading towards Bingo and reaches the cave before exploring out through another entrance and falling. Eventually, Bear regains communications with it and starts to bridge the data. This sequence of the Spot robot Bluey is a nice illustration of how the whole system works together. This begins about the time communications is lost. Bluey approaches the stairs and issues an autonomous exploration waypoint near the top step. By the time this is reached, it's seen the ground above and issues further waypoints. It continues on and reaches the edge of the subway platform. There's no further traversable ground, and the edge becomes lethal as the virtual surface below is eroded. It explores around the platform until the stairs down, which have high traversal cost, are the only remaining frontier. It plans a path down, moving backwards due to the higher traversal cost of descending forwards. It starts moving towards the rail, but turns around due to the relatively high cost and the lower cost alternatives behind. To emphasize, this entire sequence occurs out of communications range. This summarizes the object detector performance. We scored 23 points, 20 visual objects and 3 non-visual, which includes gas and the cell phone. One visual object was detected by Bluey near the end of the run. Data for this was not received in time to action. Post-analysis shows that detections were received on 2 other gas artifacts and 2 Wi-Fi cell phones, but data was insufficient to action as a detection. 3 objects were missed by the detector, 2 survivors and a cube, and the remaining 9 objects were never passed. Our conclusions in the final event include: we're obviously very happy with the SLAM performance. Overall, we're happy with the performance of the nav stack and object detector. The full suite of tools for autonomous operation, operator prioritization, and intervention were particularly valuable, and the peer-to-peer database was another key enabler. Obviously, there's still some obstacle types, such as the rails, that we need to address. Issues like avoiding these rails consumed a large amount of operator time. Working through these will be important in the future. Our integration with the Spot was very time constrained, and it wasn't really tuned to more challenging environments. The ATRs were too big for many of the tunnels. A smaller platform such as DTR would have been very beneficial. We had difficulty finding and getting to good locations to launch the drone. The railway tunnel and the end cave seen by Bingo were the plan, but it was difficult to get the marsupial launch platform there. Finally, we have to acknowledge the brilliant efforts of our deployed team. We're very happy with what we achieved through remote support. The amount of remotely guided hardware work is quite amazing and enabled the good outcome. We've noted some lessons learned across the whole program here. We've learned a lot about testing. The decision to build our own on-site test facility was really key to our performance. Having sufficiently robust platforms to enable regular tests was also key. This forced us to focus on the platforms that provided that robustness. The common sensing suite and largely common navigation stack worked very well for us and enabled us to support multiple platforms, prioritizing tuning as required. One key decision point for us was deprioritizing and subsequently dropping the hexapod, which was in part due to the remarkable capability of the tracked Titan platform. Experience with Spot shows that quadrupeds have come a really long way, but their instability in rough environments still begs the question of whether a hexapod with a similar level of investment would provide further capabilities. We've gained a lot by leveraging COTS hardware as it matured, but there was still a lot of investment needed to do that. An example of that was the comms node. Converting the Regent Wi-Fi node into a droppable comms node with appropriate antennas, dropping mechanism, and so on was a big job and took multiple iterations to get right. Likewise, the Titan platforms, capable as they are, were designed for remote control. We had to upgrade the motors and controllers to get robust autonomous performance. In our experience, this is a common story. In terms of technology, the results show that SLAM is sufficient with the deployed sensor suite and team size. There's still extensions such as trying to achieve similar results with a lower cost sensor set and scalability to larger numbers of agents. A key result, particularly shown in our cave testing, was that the local navigation performance was comparable to or better than a human. High-level autonomy, coordination, etc. is coming along, but still shows great benefit from human guidance. Working out how to provide that guidance had significant payoff, and we've only scratched the surface on what could and should be done. Finally, this shows references to papers describing aspects of the methods we've used. Several more are in preparation. Thank you for watching.